So I was going to say that so you can also say it satisfies ZF and you don't worry about P, but sort of to emphasize that we're never ever using the power set axiom in our arguments. Okay, what does X is finite mean? You could add in a natural number, but you don't really need it. X is finite can be written in this fashion, and what is phi? So, just the other way around. The range of F is an element of omega, and F is injective. You can express these things in all kinds of ways, and when you do that, you get to the point that well, but how did I prove that this was actually? And then it turns out that you use all kinds of things from ZF minus P. For example, F is a function. Well, what does it mean? Well, every member is an ordered pair. Now, what I had on the board was that Z is equal to X comma Y. So that was delta zero. So now Z is an ordered pair. Is that delta zero? Well, in fact, it is. You can actually make this a little bit shorter because you can take the u and the v from y, for example. But these are all bounded quantifiers. Okay, so every member of F is an ordered pair. So for every x for every z in F, z is an ordered pair. And then for every z, and you can also express x is the first coordinate of z in a delta zero fashion. You know, a rainy afternoon, and you can write down all the delta formulas you need to express all those easy things. So the first coordinate, you can pick it out using a delta zero formula. The second coordinate, you can also pick it out using a delta zero formula. And then you can express that if x is the first coordinate of two ordered pairs, then the two ordered pairs are the same, telling you that you have a function. You can also express that if y is the second coordinate of two ordered pairs, then the ordered pairs are the same. That'll tell you that it's injective. This is also delta zero because for every x for every u in y, there is something in v in f with its first coordinate, that thing. And for everything, the first coordinate is in x. That's all quantifying over f and members of f and members and members and members of f. This is a bit tricky. Okay, you can express omega as it is an ordinal and every member is a successor ordinal. And itself, and it's a limit ordinal. So the limit ordinal was delta 0. And then you could say, well, every member is a successor, makes it omega in a limit ordinal. You could actually you can express being a natural number in this way. Because it says that you are a successor and every member is also a successor. And this is all bounded quantifiers. So anyway, all those things are delta 0. But well, we have this one existential quantifier in here. Okay, let's erase this. This is upward absolute. Because if there is a member of M that does this, then it does it in M. If it does it in M, it does it. And so it tells you that X is finite. And this, by the way, is an example of a sigma 1 formula. Because we have delta 0, and we have one unbounded existential quantifier in front of it. Is it downward absolute? In this particular case, yes. The point being that we made M big enough so that it would contain omega, because we get ZF minus P, so it has the axiom of infinity. We stuck omega in there. So if we have a transitive set that has omega as a member, then this whole thing is absolute for it. But as soon as we have a function like that, it will actually be a member of M. Because it's a finite subset of M. It's a finite set of ordered pairs, and all the coordinates are in M because they're either in X or they're in omega. So it's a finite subset of M, and then you can show that it's just in there. The point actually is that every F that does this is in M. Because you can do all those simple operations with your sets. Let's see, what else did I want to say? Okay, there are a few things in my notes, and there are one or two things that I left as exercises, and I might just turn this into homework. Yeah.
So just when we say that X is finite is absolute, for example, we specify the M, but is there an N?
Well, that's the universe. Then,
okay.
if I'm not, if I. I mean, it's absolute between things that satisfy ZF minus the power set axiom. Because for both you need to know that. Here is one.
Are you claiming this is absolute upwards, for example?
And downwards. Well, it's downwards absolute for sure. Because if all the subsets have a minimum, then certainly all the subsets that are members of M have a minimum. Because that minimum is a member of that set itself, so that is going to be an M. The point is, if I know that R well orders A, do I know that in M, do I know that it well orders A? Well, yes, we do, because we have this. And the proof that there is an ordinal, there is one ordinal that is isomorphic to A comma R, doesn't use the power set axiom. It only uses replacement and some functions and some ordered pairs and whatnot. That function is actually unique, and it belongs to M. Because it's, well, actually, in M, it well orders R. So in M, there is a function that is the isomorphism. Oh, but there is only one, because we have found that every well order is isomorphic to exactly one ordinal, and so on. And so we have the map that sends this structure to that ordinal. Who cares about other subsets of A that are R or are not in M? This function will give them their minimum. Because it's isomorphic to something that's definitely well ordered in the real world. And so there are, so like I said, this is generally upwards absolute. And this is typically pi 1, because you say for every subset, and then the formula that expresses there is a minimum, that's delta 0 again. Because it only talks about members of A and whatnot. So there is, for every subset, delta 0. That's a typical pi 1 formula. And pi 1 goes down. Because if you know that the pi 0 thing works for everything, it definitely works for all the things that are in the substructure. And this is up. If you find an individual that does it, then it does it, because the rest is absolute. So sigma 1 formulas are nice, they go up. Pi 1 formulas are nice, they go down. Now, occasionally these go down, and especially in the case that, actually, what I showed is that the definition of well ordering is pi 1. But the characterization was there is a map that is an isomorphism, yada, 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 yada. That is sigma 1. Oh, so what are the things we are hunting for? We are hunting for statements that have a pi 1 expression and also a sigma 1 expression. And that's why you need to assume that your transitive set satisfies a bunch of axioms, because how did we usually get to the other formulation? Via some proof that used a bit of ZF. And if we're lucky, it doesn't use the power set axiom, so we know that it works in more than models of ZF, also in more general situations. And occasionally, we need to know that.
So in general, if a notion is both pi1 and sigma 1, or has a characterization in both terms, then it has a delta 0 characterization, or no?
No, we call it delta 1.
Delta 1. But so delta 1 is sufficient for absoluteness?
Yeah. Not necessary, but it's sufficient. So we call a property delta 1 if it has a pi 1 and a sigma 1 expression. Because there are no literal delta 1 formulas, because it would have to start with an existential and a universal quantifier and just one. That's a little bit problematic. But so we call it, calling a formula sigma 1 is fine, calling a formula pi 1 is fine, calling a property delta 1 is also fine, because we assert the existence of two formulas that do the thing. And once we have the two formulas and the structure is rich enough, we have absoluteness. Okay.
And does this iterate? So if you have a delta 1 formula, and then you can characterize some notion in terms of a, from both sides. You add one quantifier, you get precision. Can you keep the absoluteness as you go up?
I think this is what Juhi showed on his slides a couple of weeks back. So yeah, I think so.
Okay, I never needed that, so I didn't think about it, but maybe. Now, so what trickery? Notice I'm still talking about formulas. I'm still not talking about objects that we have in ZF. I'm only talking about, what we can do if we have a delta 0, sigma 1, pi 1 formula. Somehow we have to get rid of this for every formula this or that happens. Now, there are various ways how to do this. These two do roughly the same thing. This is Gödel's little booklet where he does the constructible universe, and of course this is Jech's book where he adapts Gödel's methods. This Koenen's book, if you read the defining definability chapter, you'll see what his trick is to circumvent talking about formulas. I decided to take Jech's Gödel's approach, and that is this. What we're going to do, we're going to talk about Gödel operations. Gödel operations are not quite unique, because in his booklet, Gödel used 8. And if you look in Jech's book, you'll see that he uses 10. And I have another book at home that uses 7. So people try to be clever and have their own variation of the Gödel operations and try to do two things at once and everything. But okay. So Gödel and Jech and other books, they write down a bunch of functions. These are class functions. So formally, I mean, they work on the whole universe of sets. Actually, so these work on the square of the universe of sets, all the ordered pairs of sets. So formally, they're formulas that express this relationship, but we pretend that we can look at them as entities, as classes. Okay. These are, like I said, these are 10 formulas. These are functions from the universe to the universe, or the universe squared to the universe. But if we were doing this the correct way, we would simply write down 10 formulas that would express these relationships. But we're using the class notation. So this one, okay, yeah, fine. We want to have products. This one, we want to be able to extract the element of relation from a product. And that's what this does. What we're going to do is going to relate delta zero formulas to compositions of these G's, and compositions of these G's to delta zero formulas. And so it's clear why we need G3, because we need to express thingy is element of other thingy. And this we want to be able to extract stuff from products, because we want to take subsets and things. Okay, complement, intersection, union, domain is useful. We want to be able to extract the first coordinates. You could say we also want to extract the range, but we can extract the range by first doing this and then taking the domain. Yay. And these two are also just sometimes I think to make things more complicated, and sometimes to make things more easy, but less complicated. But there will be times when you need to switch around a few arguments, and then you can do whatever it is that you need to do. So, for example, if I have triples and I want to extract the second coordinate, I apply this one, I don't know, once, twice, because it just goes the other way around. And then I take the domain. That kind of clever trickery. Oh, and by the way, when you go back to the first chapter of Jech's book, and I forgot to say that explicitly, and I'm looking at Yeah. Formally, an ordered triple is an ordered pair. This is on page 7 of Jer's book, for example. So we have to keep Jer's notation in the back of our heads now, because he is going to operate on this idea of ordered triple. So this is actually a complicated way of rewriting this, because it implicitly extracts the first and second coordinate of the first coordinate and then moves them around and resets them into an ordered triple. So on the surface it's a bit complicated, but okay. And the same thing goes for but we can also abbreviate this as this is also an ordered triple, because these two things are the same thing in the definition. So fine, but this is going to pop up in one or two of the arguments. So just be forewarned, and if I don't forget, I'll remind you of it later on. So these are the Gödel operations. These are purely set theoretically. These are 10 formulas, 10 classes, what you want to call them. And we just write down all kinds of combinations of the formulas that express these things. And those are the ones that we're going to be talking about. And we're going to express everything in terms of those 10 formulas.
For the domain, do we take it to be the empty set if it contains no...
Yeah. Yeah, the domain is just the set of first coordinates of any ordered pair that belongs to the set. And if there aren't any, tough. But yeah.
So this is not just convenience, right? It's where there's no like meta level. This is just a
Yeah.
way of rewriting these.
Yeah. The point is the theorem that I'm not going to prove today, because it takes up too much time. And the odd thing is, the easy, simplest formulas will take up the most of the time. There are two things, and I'll use that to explain what is coming, and then we'll do more of the details next week. Suppose you have a delta zero formula. Then you can find a composition of G1 up to G10 such that how many variables? I had n variables in my formula. conversely, so two things, and there is an equivalence here, apparently. You give me a delta zero formula, I give you a combination of the 10 operations or the 10 formulas if you want to do it if you want to work completely in terms of formulas, fine, then you can recreate that composition by way of the formulas and express this only in terms of those 10 things. I mean, the composition could be really hairy after a while, but still, it's possible. And conversely, if you have a composition like that, then you can write down a delta formula that will express this. Now, why do we want this? Well, for one thing, and here is where these functions come into their own. We have functions. We have finitely many functions. And remember what we did a few weeks ago? We were closing sets under functions. You know, we take all the images, and after countably many steps, we had a closed thing. And so if we can make a transitive set that is closed under the applications of all these functions, then it satisfies the axiom of separation for delta zero formulas. Okay, I wrote that down in my notes, and I'll try and scan them tonight. So you have, let's see. By the way, we're talking delta zero formula, so whether we stick an M on there or not is immaterial. Okay, so we somehow have to create this out of those G's. Well, so remember, I don't have too much space here, but remember what we have. We have an X, and we have a bunch of parameters, and we want to show that the members of X that satisfy this formula with those parameters belongs to M. The trick is, we're talking about these parameters. Well, these parameters come from one-element sets. We are looking for tuples that satisfy this formula. Okay, but these are always the same. It's always P1, it's always P2, it's always Pn. So the set X2, so to speak, is just singleton P1. And X3 is just singleton P2. Okay. Say X is X0, and then we start to count from X1 up. So this one will be all the tuples that satisfy the formula. And then the set that we're looking for is what you get when you apply domain, 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 domain to it n times. Because then you get the first coordinate. I mean, domain once means you throw away the Pn. Domain twice, Pn minus 1. And domain n times, you're just left with u. So, and this is domain n times composed with this G, this mysterious G. We're in M because M is closed under the mappings. Now, so what did we do? We found a way to talk about all the delta zero formulas anyway, without mentioning them. Because we're not going to say, let's take a transitive set that satisfies delta zero separation. No, we're going to say, let's take a transitive set that is closed under the action of the mappings GI. But we, on the outside, on the meta level, now know we can stick any delta zero formula in there that we want, and we get this result. And we can use that to say, well, this is going to happen in that particular structure. And the other thing is, this tells us that the Gödel operations are absolute for transitive sets that, actually for transitive sets, period. Because delta zero formulas are absolute. So what do we know? And that's, I'll leave it there. What do we know? And that's important for next time. If we calculate these things, we can calculate them in the real world, in V, or we can calculate them inside our model M, and the result will be the same. And I hope that I will have the, let's say, the willpower to keep saying this, because there comes a moment when you're doing this kind of thing, you say, okay, fine, I don't bother anymore with saying, oh, but because it was absolute, this or that happens. You tend to forget. If it gets too familiar, you say, oh yeah, right, that happens, fine, it's in M, done. But you need to, this absoluteness business is one of the, to me, for me, was one of the hardest things to get into my head. I mean, okay, you have seen it now, you know what it means, but to get it, say, in your your subconscious, that's another thing. You need to be able to work with it subconsciously almost, because it's not really the main thing. It's just a tool, but it's a tool that needs a little bit of it needs practice to work with it. And believe me, I have stumbled enough to know that it takes some time to work with it, to learn to work with it. That's the only warning I can give. So next time we'll just pick up this thread, and the thing is, the trick that we're going to play is we're going to redefine the definable sets by using delta zero formulas only, but with an extra trick. And then, of course, we don't say we use delta zero formulas. We say we close under the mappings G. And then it says closing under the mappings G is the same as making the definable sets using delta zero formulas. And that'll be it. And now Paul has a problem.
So since the G's are just abbreviations for formulas, we're not moving between the theory and the meta theory or whatever. What advantage do we get from expressing something using in terms of G's? I mean, we can't quantify over the G's, can we? Any more than we can over formulas.
Yeah, but we only have 10 formulas representing the G's, and we can express, say, compositions of the G's using sequences of instances of these G's. And those instances, since there is only 10 things, we don't quantify over the G. We quantify over the G's simply by saying it's G1 or it's G2 or G3 and that's 10, that's 9 ors, and that's delimited. You could say for I is 1, 2, 3 up to 10 we do this, or you can say G1 or G2 or G3 or G, and that saves the day.
So the G's are finite, that's good, and then the composing that can also all be done in the theory.
Yeah, because composing the G's is just making very complicated formulas using the formulas that describe the G's. If you want to describe G1 after G2, you say, well, you say X is G2 of G1, although it doesn't really make much sense, but it's sort of like, first you describe Z is, you write down the formula that says that Z is the product of X and Y, and then for those things you express that they are the result of doing G1 in the formula for G1. And I mean, that's why we do things by induction on complexity, because if we do one, yeah, it works. If we do that one, it works. If we do that one, it works. Fine, it works all the time, and we don't really bother about the exact formula that we're using. That's going to be the thing.
So, what is the relation between this hierarchy of formula and this